This is the cache section of the MIPS software training course. In this section, I'll cover the dimensions of the cache and what make up the cache size, how things are looked up in the cache, what types of cache policy you can set, what non-blocking loads are, the initialization of the cache management such as cache flushing, what virtual aliasing is and how to avoid it, what the prefetch instruction does, and cache exceptions. MIPS cores have separate instruction and data caches so that an instruction can be read and a load or store done simultaneously. Except for the 4KE, all caches are four-way set associative. For the 4KE, there is a choice from a direct map cache to a four-way set associative cache. More ways of associating a cache line within a page to physical memory usually means less cache thrashing. Cache line size is fixed at 16 bytes for a 4KE and 32 bytes for the rest of the cores. Lines per way will determine the cache size. These are a power of 2 starting from 64 to 512. This corresponds to a cache size of 8 to 64K. Sets per way is a superset of a line where a cache line is the actual data and the whole set includes the cache tag and status bits. The size of the cache is equal to the number of ways times the line size times the number of lines per way. All cache choices regarding cache sizes and the number of ways are options configured when the chip is built and are not changeable at runtime. This example will give you background information on how the cache works. It will show how data is retrieved from the cache. The example assumes a 4K page size and a cache with 4 ways for a total of a cache size of 16K. Each virtual program address can be broken down into 3 parts: the virtual page number, the index into the cache array, and the byte index into the cache line. Caches are virtually indexed and physically tagged to allow them to be accessed in the same cycle that the address is being translated. This means that while the MMU is using the virtual page number to get the physical page number, the cache controller is using the index part to locate where in each way of the cache the line might be stored. So once the translation is made, the controller can compare the translated physical page address to the physical tags in each way to see if there's a match. If there is a match, we have a cache hit and the fetch, store, or load is completed. If not, it's a cache miss and the processor will call on the bus interface to get the cache line from memory. I am going to go into the cache policy, which is determined by the TLB entry for the page that contains the memory access. This is set up by the C field in the entry low register when the TLB entry is written for each page. The CPU uses these bits to figure out what to do. The page can be marked uncached, which would cause the CPU to go directly to memory for the load or store or instruction fetch. If the page is cacheable, these bits will set the cache policy, which I'll cover next. I'm not going to go into the TLB entries because they are covered in the TLB section of this course. The first cache policy we're going to go into is write through with no write allocate. Here is what it does on a load or instruction fetch. First, the cache is checked to see if the data or instruction is in the cache. If it is, the request is filled from the cache. If it isn't, the cache line worth of data is read from memory and then placed in the cache, and the request is filled simultaneously. On a store, search the cache to see if the target address is cache resident. If it is resident, the cache contents are updated and main memory is also written. If the cache lookup misses, only main memory is written and no cache line is allocated. Important points here are: there is no read of a cache line on a miss, therefore no cache line is allocated. And the cache never contains dirty data, thus there are no write-backs on cache evictions. There is another flavor of write-through cache that uses a merge buffer. With merging, if a line hits in the cache is updated and the data is merged into a 32-byte collapsing write buffer. If the line misses in the cache, the data is written to the merge buffer. This lessens bus traffic by gathering write-through bytes into a buffer the size of a cache line and writes it when it's full or out of the physical address range of the current line. If you are doing a DMA from memory, you will need to ensure that the last write is flushed out of the cache into memory. The prefetch instruction with a nudge option will accomplish this. Merging is controlled by the MM bit, bit 18, in the coprocessor 0 config register number 16. Merging is set to 1, meaning on at reset. Another cache policy you can use is called write back. For write back cache, on a store, the cache is searched to see if the target address is cache resident. If it is resident, the cache contents are updated. If the cache lookup misses, the cache line is read from memory, then the new data being stored is merged into the line and stored into the cache. Important points are: cache lines are always filled from memory on a cache miss. Main memory is never updated on a store. If there are no way entries free when a new line needs to be put into the cache, a line needs to be evicted from the cache to make room for the new line. The line will be evicted based on a least recently used basis. If the evicted line is dirty, meaning it contains data not in memory, then that line is written back to memory. In most cases, the data caches are non-blocking, allowing for an instruction stream to continue executing until an instruction that is dependent on the missed data is executed. Then the processor will stall until that data word is loaded from memory. The 4KE core is an exception to this. The data cache on a 4KE will block until the data word is loaded from memory. It will not continue to execute non-data dependent instructions. Some cores can have more than one cache miss outstanding at a time. The 24K, 34K, and 1004K can be configured at chip build time for 4 or 8 outstanding data cache misses. The 74K is not configurable and has 4. Let's talk a little bit about the cache instruction. The cache instruction has two arguments, the virtual memory address and the operation to be performed. I'll show you more about the actual assembly code for the cache instruction and explain how the virtual address is used in an upcoming example. Since the example only uses one cache operation, I'll discuss all types of cache operations that can be performed here. Cache operations fall into 3 different types. The first is the index operation. For an index operation, the virtual memory address is used to index each byte of the cache. I'll cover what the address looks like in just a bit. This breaks the cache down into a multi-dimensional array where each cache way would be the column in the array and the rows would be the cache lines and then the bytes within the cache lines. The example code will be using the index store tag operation to initialize the cache. Next is the hit operation type. For this operation type, the operation is only carried out if the virtual address hits in the cache, indicating that the cache contains valid data for that address. This operation is good when you need to flush dirty data at a specific virtual address. Last, there is the address operation type. For this operation type, the operation can only be carried out if the virtual address misses in the cache, indicating that the cache does not contain valid data for that address. These operations, such as data cache line fill or instruction fetch, or locking data or instructions into the cache so that valid lines aren't normally replaced. On power-up, reset, and soft reset, the cache may be in a random state. Before it is used, it must be initialized to a known state. In this section, I will go through what it takes to initialize the cache. Along the way, I'll introduce you to the cache instruction and coprocessor 0 configuration registers that are needed to control the cache. The code will show you how to find the total number of cache sets in the cache. Remember, a cache set is a combination of cache tags and cache lines of data. Once the number of cache sets are known, the code will loop through the cache, clearing the cache tag of each set, making the set invalid. The code is going to use coprocessor 0 configuration register 1 to get the cache dimensions. I'll go through the bit fields the program will be using. The IS and DS fields encode the number of sets per way for the instruction and data cache respectively. The field values start with 0, indicating 64 sets, and as the value increases, the sets increase by a power of 2 with a maximum of 4K. The IL and DL fields encode the cache line size, or the amount of bytes of data each set holds for the instruction and data cache respectively. Legal values can be from 0 to 6. 0 would indicate no cache presence, and a 1 indicates 4 bytes, and as the value increases, the number of bytes increase by a power of 2 to a maximum of 128. The IA and DA fields encode the number of ways for the instruction and data cache. The field value of 0 indicates one way, and as the value increases, the number of ways increase by 1. Not all values are supported for all cores. You should check your core's software user's manual for your particular core for more information on which values are supported by your core. The code will use configuration register 1 to compute the total number of sets in the cache to loop through and initialize each set's cache tags. The code uses the move from coprocessor 0 instruction to get the value of the config1 register into the general purpose register 10. The extract instruction is used to extract the instruction cache line size. It uses the config1 register value that was saved in general purpose register 10 starting at bit 19 and extracts 3 bits to the least significant bits of register 11. It is then tested to see if it is 0. If it is, it means there is no instruction cache, so it will branch ahead and not initialize it. Now the code decodes the line size to get the actual number of bytes in a line. It does this by shifting 2 to the left by the encoded line size value. Now the code extracts the number of sets per way from the value read from the config1 register that was stored in the general purpose register 10. It does this by using the extract instruction. The extracted value is converted to the actual number of sets per way by shifting 64 to the left by the extracted value. The number of ways is extracted from the config1 register value using the extract instruction. The code then adds 1 to the value to get the actual number of ways. Now the number of sets per way are multiplied by the number of ways to get the total number of sets in the cache. This will become the number of loops to be performed to initialize the cache. The general purpose register 14 will be used to index into the cache. The trick is this needs to be a virtual address. The virtual address that is the index into set 0 of the cache is 80 million hex. This works out because the virtual address is in kseg0. If you recall, kseg0 is in the virtual address range of 80 million hex up to a million hex minus 1. This directly maps to physical address 0 through 2 million hex minus 1. So the CPU translates the virtual address 80 million hex to physical address 0. Physical address 0 will always index into set 0 of the cache. The code loads register 14 by using the load upper immediate instruction with 80,000 hex. This instruction sets the upper bits to 80,000 hex and clears the lower 16 bits. Clearing the tag register does two important things. It sets the physical tag address called ptaglow to 0. This ensures that the physical address bits are zeroed out. It also clears the valid bit for the set, which ensures that the set is free and may be filled as needed. The code uses the move to coprocessor 0 instruction to move the general purpose register 0, which always contains a 0, to the tag registers. You need to consult your programmer's manual for your core that you're using to see if the tag high register also needs to be cleared. The code is almost ready to start the loop through the cache. This move instruction puts the total number of sets that the code computed into register 15, which will be decremented each time through the loop. Here is the format for the cache instruction. The op field is 5 bits. It contains the cache type and the cache operation to be performed. Bits 0 and 1 encode the cache type. 00 for a level 1 instruction cache, 01 for a level 1 data cache, 10 for a level 3 cache, and 11 for a level 2 cache. Our MIPS core does not support a level 3 cache, and level 1 and 2 caches are optional. Bits 2, 3, and 4 encode the cache operation. For the upcoming example, I will be using index store tag operation on the level 1 instruction cache, so the op field is coded with an 8. The first 2 bits are 00 for level 1 instruction cache, and the operation code for an index store tag is encoded as a 010 in bits 2, 3, and 4. Here is the actual cache instruction code. To review, the cache instruction takes 2 arguments. The base address, which we initially set to 80 million hex to address set 0 of the cache. The operation code, which in this case is index store tag of the instruction cache. The assembly line is tagged with a 1 in column 0. This gives the code a place to branch back to start the loop again. I want to explain one slightly tricky thing that will happen in the code. The index type of operation can be used to address a byte in the cache in a specific way of the cache. This is done by breaking down the virtual address argument stored in the base register of the cache instruction into several fields. The size of the index field will vary according to the size of the cache way. The larger the way, the larger the index needs to be. In this example, the combined byte and page index is 12 bits because each way of the cache is 4K. The way number is always the next 2 bits following the index. In this example, the code does not explicitly set the way bits. Instead, it just increments the virtual address by the cache line size, so the next time through the loop, the cache instruction will initialize the next set in the cache. Eventually, this increment has the effect of setting the cache to index 0 of the next way of the cache because it overflows into the way bits. Now all the code needs to do is loop maintenance. First, decrement the loop counter. Then, test it to see if it's gotten to 0. And if it has, don't branch back to label 1. The branch delay slot, which always gets executed, is used to increment the virtual address to the next set in the cache. Now let's talk about cache maintenance. When working with cache data buffers where DMA is involved, there are some necessary steps your code needs to take to ensure data integrity. If you are starting a DMA operation to DMA data out of memory, and the data is stored in cache write-back pages, some of the data may not be coherent with main memory. So before the DMA starts, the data must be forced back to main memory using a cache instruction to flush it from the cache to main memory. If you are starting a DMA operation to DMA into a cached area of main memory, you will need to invalidate those addresses in the cache. If you don't, the cache could hold valid data for that buffer range. The upshot would be that the new data that the DMA brought into the main memory will not be brought into the cache. Other cases you need to worry about cache coherency are when you write instructions, usually done by a loader or an OS, when you insert a breakpoint, usually done by a monitor program controlled by a debugger, or when your code is self-modifying, which is done in many of the Java accelerators. In these cases, the code written to the cache using a store instructions will write data to the data cache, but not the instruction cache. The instruction cache may already contain valid instructions for the memory you are modifying, so it will not fetch new instructions. First, data cache and main memory must be made coherent, and then the area in the instruction cache that contains old instructions must be marked invalid. There is one instruction that handles this for you called synci. This instruction takes the address of the instruction that you are changing and flushes the data cache line that contains the instruction out to main memory, and checks to see that the same line in the instruction cache has been invalidated. So the next time the instruction is fetched, it will miss in the instruction cache and the cache line will be brought in from main memory. There is also a macro provided with most toolchains called MIPS synci instruction that can be used from C code. There is some help if you are writing code in C or if you just want to see more examples. These files should be included in your toolchain. If not, contact support@mips.com and request them by name. I'm going to cover what's in some of these files next. There is a function that sets up global variables with the cache dimensions called MIPS size cache. Many of the other functions that follow rely on these global variables being set, so before you can call them, you must call this function. These are the global variables it sets. The MIPS init cache function will do all the steps I described earlier to initialize both the data and instruction caches. It will also set up the global variables with the cache dimensions, the same as the MIPS size cache function. The MIPS sync iCache function will use the sync I instruction to synchronize the iCache after the instruction stream has been modified or loaded programmatically. It takes two arguments, the virtual address of the instruction to start with and the number of instructions to synchronize. The MIPS clean dcache is ideal for use prior to starting a DMA that writes out to a device from main memory. It will ensure the memory contents have been updated and in sync with the cache for the designated memory range. It takes two arguments, the virtual address of the data to start with and the number of words to flush. The MIPS clean dcache no write is ideal for use prior to starting a DMA that reads data from a device into main memory. It will ensure the cache lines are invalid for the designated memory range. It takes two arguments, the virtual address of the data to start with and the number of words to invalidate. The MIPS flush dcache function writes back all the dirty cache lines and invalidates all of the cache lines. This can be used before a warm boot. Let's talk about virtual aliasing. Virtual aliasing happens when the number of sets in a way of the cache is larger than the number of sets needed for a size of a memory page. For example, let's assume a 32K cache with 4 ways and a 32-byte line size. That would mean that each way is 8K of the cache. To index an 8K way, it takes 256 indexes, given a 32-byte line size. That's 81,092 divided by 32 bytes per line, which equals 256, or 8 bits. Bits 5 through 12 for the cache line index. To index a 4K page, it takes 128 cache lines. That's 4,096 divided by 32 bytes per line, which equals 128 cache lines, or 7 bits. Bits 5 through 11 for an index into the page. This leaves bits 12 through 31 for the physical tag. This causes the tag and the index to overlap at bit 12. This overlap can mean that two different virtual addresses mapped to the same physical location in memory can have two different entries into the cache, so the cache can end up with two different data values for the same physical memory. Using the same cache dimensions I just showed you, one cache way would look like this. Each way could fit two 4K pages. For this example, the first virtual address is address 0, and it translates to physical address 0. It will look like this. As you can see, the virtual address is made up of 12 bits to index into the page and 20 bits of virtual address to be translated by the TLB to a physical address. In this case, the page translated to physical address 0. The cache index, which I explained previously, is 8 bits. Bits 5 through 12, which for this address indexes to index 0 of the cache. Now let's look at a second virtual address. The 20 bits of virtual address translated by the TLB is translated to physical address 0. The cache index of 8 bits, bits 5 through 12, for this address will index into 128. Both indexes end up with the same physical tag. The easiest way to avoid aliasing is to create your core using the optional hardware anti-alias option. There may be a small difference in the clock rate you can achieve by using this option. To see if your core was built with this option, you can check bit 16 of CP0 config 7 register. If you don't have the hardware option, the next easiest thing would be to make sure your page size is at least as large as the cache's way size. Another way is to always map overlapping bits straight through. In the example we just went through, you would avoid creating the virtual to address. In most cases, aliasing happens when you are sharing data between processes. So another way to avoid them is to align shared data buffers, virtual addresses, on a way boundary. For example, if your way size is 8K, then align your buffers on an 8K boundary. You can also flush and invalidate shared buffers at a context switch. By the way, you should not have to worry about the instruction cache since it's read-only. Also, versions of Linux from version 2.6.8 and upward have been designed to avoid data cache aliasing. Now let's discuss prefetching. Data prefetching is like what some fast food restaurants do. They cook food ahead of time, anticipating the demand so that they can shorten the customer wait time. Of course, the amount of food they can cook ahead will depend on grill capacity and other needs for the grill. Such is the same as your data needs. You can use the prefetch instruction or the macro function provided in CPU.h to get data into the cache ahead of time, anticipating the code's need for the data. For example, when you're doing a memory copy from one buffer to another, the prefetch instruction tells the CPU to get the data into the cache if it does not interfere with any other data bus operations. Prefetching can be tricky, because while you may think it should increase the performance of your code, it may not. It'll depend on your cache resource needs. For example, sometimes you can have a lot of frequently used data, and if your code does a lot of prefetching, it can force this data out of the cache. So you may increase the performance of your memory copy, but decrease the performance of something else. The frequently used data could also be forcing your prefetched data out of the cache before you actually use it. As a side note, this could be a sign you need a larger cache. Here's a few simple rules to follow. Prefetching, to be effective, needs to be done far enough ahead of time so that the data is in the cache when needed. For example, in a copy loop, you may need to be prefetching data several loop iterations before it's needed. One caution, be careful when you are using data that is being put into memory by a DMA device. In your effort to prefetch data far enough ahead of its use, the code could get ahead of the DMA operation, and the data prefetch would not be fetching the new data. I am going to show you an example of prefetching in a memory copy to give you an idea of what you may need to do. The code is simplified to highlight the prefetching being done. If this were an actual mem copy, the code would need to have some logic to align the copy to a cache line boundary. It would also need to decide what the minimum number of bytes would be to make the prefetching useful. Here are the arguments used in the example. I have also included how to use a performance counter register to measure how many cycles the copy takes so you can see how well the code is functioning. For your system, you will need to experiment to see what gives you the best results. There are just too many variables to be able to calculate how prefetching is going to affect your code on your system. Here is an example of prefetching. First, I am going to use an internal counter register to determine how long the copy took so I can judge the performance of the prefetching. Each of our cores contains at least 2 performance counters. The performance counters are located in coprocessor 0 register 25. Each counter is broken down into 2 CP0 registers. The even select register is the control register, and the odd select register is the actual counter. For example, let's say the core we are using has 2 performance counters. Coprocessor 0 register 25 select 0 is the control register for counter 0, and select 1 is the counter for counter register 0. The second counter's control register would be coprocessor 0 register 25 select 2, and the counter would be select 3. In the code, you will need to tell the CPU what you want to count. I want to count cycles. Writing a 2 to the performance counter 0's control register programs it to count cycles. I do this by loading a 2 into register T1 and using the move to coprocessor 0 instruction to move to coprocessor 0 register 25 select 0. I use the EHB instruction to ensure the register is written before I go on. Then I clear the count in the performance counter by moving register 0 to coprocessor 0 register 25 select 1. For this code, I decided to try prefetching 512 bytes ahead to see what numbers I get. I have paired the input and output prefetches. The input prefetch will prefetch a cache line into memory. The output prefetch will prepare the cache for writing an entire line without the overhead involved of filling the line from memory. I'm going to continue with prefetch instruction until I have given enough to prefetch 512 bytes. At the point I will be looping back to, I will prefetch the next lines to always keep 512 bytes ahead. I have a second branch point I will branch back to when I have prefetched to the end of the buffer. Next, I will load the whole cache line from the input buffer, and then increment the base address by the line size. Now store a cache line's worth of data to the destination address and increment the next address to fetch ahead. The code checks to see if we have prefetched the entire buffer yet, and if we have not, branch back to the prefetch point. In the branch delay slot, that will always get executed no matter if the branch is taken or not, the code increments the output buffer pointer by a cache line size. The code will reach this point once it has fetched all it can but still needs to copy the last final 512 bytes. It checks to see if there is more to copy and will branch back to the non-fetch point if there is. When the copy is done, the code reads the performance counter to get the number of cycles it took to do the copy and puts it into the return register, then returns to the calling function. You can experiment with the code by changing the number of prefetches done ahead to see what gives you the best numbers for your system. There are two macros in the cpu.h file that allow you to use prefetch from C code. The first is the MIPS prefetch macro, which you would use to prefetch memory from a source buffer into the cache. For the memcopy case, the adder argument would be set to the virtual address of the line you want to fetch. RW will be set to 0, and locality would be set to 0. The MIPS prepare for store macro should be used for the output buffer, so no time will be lost reading in data that will just be overwritten. It takes the virtual address of the store line. Let's talk about cache exceptions. The cache can generate exceptions. Cache exceptions will depend on your hardware. If your cache is designed to report errors, it can do so by causing a cache exception. Cache error detection is implementation dependent. If your cache has parity detection, it will generate a cache exception when it gets a parity error. In general, a parity error in the cache is fairly serious. One problem is the exception is imprecise, which means it may be difficult to determine which instruction the data belongs to, or in the case of the instruction cache, which instruction coming up has the problem. If your code has error correcting hardware, the hardware will correct the first error without generating an exception. It will generate an exception if there are uncorrectable errors. A cache exception always vectors to a non-cached virtual address in KSEG1. On boot, this address is BFC00300 hex. Once the boot finishes initialization, it should set the boot exception vector bit. This changes the cache exception vector to A0000100 hex. There is a separate status register for cache errors called the Cache Error Register. This is coprocessor 0 register 27. This chart breaks down the cache error register. One thing to keep in mind, it is somewhat implementation dependent. The implementer of your chip will make the decision to include cache error logic or not. That person will also determine which parts of the cache error register to support. This is another coprocessor 0 register, number 26, the error control register, that plays an important part in controlling the cache parity and of telling you if the core detected another cache error while the exception code was in the process of handling a cache error. Your code can use the PE bit to determine if the core supports cache parity. If the code writes a 1 to the PE bit and reads a 0, it means that there is no parity support in the cache. This bit is set to 0 when the core boots. Once the cache has been initialized, the code should write a 1 to this bit to enable cache parity. The FE bit is set to indicate the first instance of a cache exception, and the SE bit is set when the core detects a second error before the first error has been handled. There are other control bits in this register that can be used for cache testing. Check the Software User's Manual for more information. This ends the cache section.